All right. I mentioned in class that I would do a little extra bit of notes on the motivation for why the Jacobian takes the form it does. So 14.8, we'll call it a supplement. All right, before I go into the motivations, not really a proof, just kind of a sketch of why it takes the form it does, I wanted to, we mentioned in class transforming double integrals from rectangular coordinates to polar coordinates. We talked about this similar thing for cylindrical coordinates, for triple integrals, and for spherical coordinates. I just wanted to apply the Jacobian to the example of polar coordinates, just so you see that how what we talked about with polar coordinates comes out of the Jacobian as well. So in polar coordinates, we made the transformation. Our transformation was x equals r cosine theta and y equals r sine theta. So rather than u and v, in this case we're using r and theta. So our Jacobian dxy dr theta is going to be our determinant dx dr, which is cosine theta, dx d theta, which is minus r sine theta, dy dr, which is sine theta, and dy d theta, which is r cosine theta. So that's going to be our Jacobian. When we form this determinant, we get r cosine squared theta plus r sine squared theta. We factor out the r, we get r cosine squared theta plus sine squared theta, and our Jacobian is just r for polar coordinates. So for our transformation from rectangular to polar coordinates, our Jacobian is r. Just like we talked about when we went through the argument of the polar rectangle and talked about our area element that way. So we end up at the same place. All right, now for our motivation. We're going to look at a rectangle in the UV plane. So we've done some kind of transformation. We've got a rectangle in the UV plane. So here's my UV plane. And we have a rectangle here. And I'm going to draw the rectangle, and we're going to label the coordinates of the vertices of the rectangle. So I'm going to get my rectangle here. So there's my rectangle, and we're in the UV plane. We're going to say this vertex just has coordinates UV. And our rectangle, we're going to say our rectangle is small. So the coordinates of this rectangle, we're just moving up by a small amount, v plus delta v. This is going to be u plus delta u, v. And this one we have u plus delta u and v plus delta v. And we're saying that x is some function g of uv, and y is some function of uv. After the transformation, so we're transforming, we're looking at kind of the reverse transformation. We're looking at what this region is in the xy plane. So if delta u and delta v are small enough, we have approximately a parallelogram in the xy plane. We're saying delta u and delta v are small enough. We have approximately parallelogram in the xy plane. So let's draw that approximate parallelogram in the xy plane. So here's our xy plane. So we've done a nice transformation. It transforms this region in the xy plane to a rectangle in the uv plane. So there's y, x. So we have some kind of approximate parallelogram. So we have sides that look like. So, and we're saying this is approximately a parallelogram. And I'll label the vertices here M, N, P, and Q. And I'm going to draw the tangent vectors to the sides of this approximate parallelogram at point N. So we'll draw some vectors. I'll do those in red. So here's a tangent vector going off this direction, and a tangent vector going off that direction. And the coordinates, we're just going to label the vertex here at M, we're at X, Y. And I'm going to call this vector T2, and this vector T1. So we have these tangent vectors at point M. The one, T2, is tangent to this curve between M and Q, and T1 is tangent to this curve between M and N. And I'm going to write the coordinates. We're interested in the coordinates of our vertices going along this direction and going along this direction. We're going to make a comparison between the tangent vectors and the change between our coordinates between M and Q and between M and N. So vertex M is at the point X and Y. And I'm going to write that in terms of its dependence here, G of U comma V and H of U comma V. Point N, we're moving a little bit this direction, a little bit this in the X direction, a little bit in the Y direction. So point N is going to be G of U plus delta U comma V, and my Y coordinate is H of U plus delta U comma V. So we're just talking about the coordinates here. We're writing these our coordinates, our x and y coordinates in terms of our coordinates in transformed, in the transformed coordinate system. And then point Q is going to correspond to this coordinate here. So point Q is going to be g of u v plus delta v and h of u comma v plus delta v. So these are x, y coordinates in terms of the transformed coordinates. Well, t1 in the xy plane, we can write an expression for that vector in the xy plane. It's going to be du dx, or I'm sorry, dx du I hat plus dy du j hat. We're moving in the u direction. And t2, the second tangent vector, is going to be dx dv I hat plus dy dv j hat. And dx du, partial of x with respect to u, is dg du, because x is a function of g, x is g of u and v, and that's approximately equal to g of u plus delta u comma v minus g of u comma v divided by delta u. This is approximately the derivative with respect to u. And similarly, dy dv dy du is dh du, which is approximately h of u plus delta u comma v minus h of u v over delta u. So this gives us a way to approximate our vector t1. We could write similar expressions for t2 for the derivatives of x and y with respect to v as well. Similar expression. I'm not going to write that whole thing out, but these are our expressions for our partial derivatives and our approximation for those partial derivatives. All right. Now, if we look at the coordinates on the edges of our approximate parallelogram, we're going to see that, and we're just looking at the change in the coordinates here from m to q and from the m to n. We see that t1, I'm going to look just at t1. The argument for the second tangent vector t2 is similar. So for t1, we're going to look at the change from m to n, and we would look at the change from m to q for t2. So the arguments are similar. t1 is approximately, looking at the coordinates, t1 is approximately equal to the change in the x coordinate, which is g of u plus delta u comma v minus g of u comma v I. That's my x component. That's how much we change moving in the x direction. And the change in the y direction from m to n is, I'm going to move that down to the next line, plus h of u plus delta u comma v minus h of u comma v. And that's how much we've moved, changed in the y direction. So that's our y component of t1. Well, this expression, t1, if we look back at our partial derivatives, this expression for t1 is, so t1 is approximately dx du delta u times I hat plus dy du j hat. So we multiply this by delta u, we get our I component. We multiply this by delta u, we get our j component. I forgot my delta u. We get our j component when we multiply this quantity by delta u. So there's our approximation for t1. Similarly, we can approximate t2. We would go through the same argument, writing an expression for t2 in terms of the partial derivatives and in terms of the change in the components as we move along the side of this approximate parallelogram. So t2 is approximately, going through using a similar argument, is going to be dx dv delta v I hat plus dy dv delta v j hat. Well, those are our approximations from t1 and t2. The area of this parallelogram, and again we're saying delta u and delta v are very small, so the area of this approximate parallelogram is going to be the cross product, the magnitude of the cross product of these two vectors. So we're going to form the cross product of t1 and t2 and find the magnitude of that cross product. Switch pages here. So we're going to approximate the area of that small, almost parallelogram by the cross product of t1 and t2. The magnitude of the cross product. So we're going to form that cross product. So we have dx du delta u. So I forgot my i's, j's, and k's. We have I, j, k, dx du delta u, and dy du delta u, zero, and then the same for our y components. I'm sorry, t2 dx dv delta v and dy dv delta v is 0, and we're going to form that cross product. When we form this cross product, we end up with the approximate area of that parallelogram in the xy plane is our Jacobian. times delta U and delta V. And we sum over the small delta U's and delta V's in the region, and then that's how we end up with the result of our Jacobian. So we're approximating the area in the xy plane with the cross product of the tangent vectors, and we end up with this factor, which is our Jacobian, times delta U, delta V. Sum as delta U and delta V get smaller, and we end up with our result. So that's the motivation for where the Jacobian comes from, why it takes the form that it does. Not a formal proof, but a good outline of how the Jacobian takes a form that it does.